The universe is supposed to follow a strict set of rules, yet astronomers have found a galaxy spinning so fast it should have torn itself apart, a cosmic rebellion that defies our understanding of physics. By the end of this journey, you will see reality itself in a new light as we uncover what happens when the cosmos breaks its own laws. We will explore why empty space might be pushing the universe apart and how particles can communicate instantly across vast distances. What does it truly mean when nature itself refuses to follow the script for centuries? This cosmic rulebook seemed absolute. Isaac Newton gave us the law of universal gravitation, a force that dictates the fall of an apple and the majestic orbit of planets with mathematical precision. Later, Albert Einstein rewrote our understanding of space and time, showing that gravity is not a mysterious pull but the curvature of the cosmos itself, a fabric woven by mass and energy. These are the pillars of classical physics, a framework so robust it lets us predict eclipses 1,000 years into the future and send probes to the farthest reaches of our solar system. We built our understanding of reality on this foundation of order, where every action has an equal and opposite reaction, where energy is conserved, and where cause always precedes effect. It is a universe that runs like a perfect, predictable clockwork. But what if the clockwork is merely a facade? The deepest investigations into reality began to reveal that these foundational laws are not the final word. They are the rules for the world we see and touch, yet they begin to fray at the edges, at the extremes of the very small and the immensely vast. This established order, for all its power, is a surface layer. And beneath it, a more chaotic and mysterious reality waits, its rules not yet fully written. Our cosmic clockwork first showed a crack not in some distant, exotic realm, but in the familiar pinwheel of a spiral galaxy. The mathematics were clear. A galaxy's rotation should mirror our solar system, where inner planets like Mercury whip around the Sun at blistering speeds, while outer worlds like Neptune drift in a slow, stately orbit. This is the simple, predictable dance of gravity. Stars on the outer edges of a galaxy, far from the central bulge of mass, should be laggards, moving much more slowly than their inner cousins. Yet when astronomers like Vera Rubin meticulously measured the velocities of these distant suns, they found something astonishing. The stars, whether close to the brilliant center or out in the sparse, dark fringe, were all hurtling around at nearly the same breakneck speed. It was as if every car on a vast circular highway, regardless of whether it was in the inner or outer lane, was traveling at exactly 100 miles per hour. This defied every calculation. The visible mass of the galaxy, all its stars and glowing gas, was simply not enough gravity to hold these speeding outer stars in place. They should have been flung off into the void, their trajectories flying apart like sparks from a pinwheel, but they were not. The galaxy was spinning as a single, solid plate, a cosmic rebellion against Newton's ancient laws. The only explanation was that something else was there, something invisible and massive, weaving a far stronger gravitational web than anyone could see. This was the first compelling evidence for dark matter, a ghostly substance that does not emit or reflect light, yet whose gravitational grip is the only thing preventing galaxies from tearing themselves apart. This discovery of missing mass was a profound shock to our understanding of the cosmos. It proved that the universe we see is only a tiny fraction of the universe that is. What other invisible architects are shaping reality, hidden from our sight but undeniable in their influence? This ghostly dark matter revealed a cosmos built from shadows, but the rebellion runs deeper still. What if the universe's ultimate rule, the cosmic speed limit itself, could be broken? Einstein's theory of relativity established that nothing can travel faster than light. This is not just a suggestion, it is a foundational pillar of modern physics, woven into the very fabric of space and time. Yet theoretical physicists have long toyed with a hypothetical outlaw, a particle they call the tachyon. By its very definition, a tachyon would be born moving faster than light, living its entire life on the other side of that universal speed limit. It is a concept that exists only in mathematics, a ghost in the equations, but its implications are staggering to consider. If such a particle were real, it would not simply be moving fast, it would be operating under a completely different set of physical laws. The energy required to accelerate an ordinary object to the speed of light becomes infinite, an impossible barrier. But for a tachyon, the reverse might be true. It could require infinite energy to slow down to the speed of light. This turns our intuitive understanding of motion completely on its head. The most profound consequence, however, involves time itself. According to relativity, if an object could travel faster than light, from certain perspectives it would be moving backwards in time. This opens the door to paradoxes that shatter logic. Imagine a tachyon carrying a message. It could arrive at its destination before it was ever sent. An effect could precede its cause, creating a universe where history could rewrite itself. While no tachyon has ever been detected, and most scientists believe they are mathematical curiosities rather than real entities, the very fact that we can conceive of them forces us to confront the rigidity of the rules. We are not just testing the universe with our telescopes, we are testing it with the very limits of our imagination, probing the boundaries of what is possible. And if the rules of cause and effect can be so directly challenged, what other fundamental truths might be up for negotiation? This line of thought inevitably leads us to another energetic paradox, one that suggests the very vacuum of space is not empty at all, but seething with a mysterious, repulsive force. This uniformity of the universe presents a paradox so deep it challenges the very story of the Big Bang. Look at the night sky in any direction, and you will find a cosmos of startling sameness. The temperature of deep space, measured by the faint afterglow of creation known as the cosmic microwave background, is identical to within 1 part in 100,000, whether you look left, right, up, or down. This seems reasonable until you realize those distant regions of the sky should be complete strangers to one another. According to the standard Big Bang model, there simply has not been enough time since the beginning of everything for light or heat or any influence to have traveled between them. Think of it like walking into a vast, crowded room and finding that every single person, even those on opposite sides who have never met, is wearing the exact same outfit, down to the same color socks. This is not just a coincidence, it is a cosmic conundrum known as the Horizon Problem. How could parts of the universe that have never been in contact possibly agree on a common temperature? It is as if the universe broke its own rule that nothing can travel faster than light to achieve this perfect equilibrium. The solution proposed by physicists is as radical as the problem itself, a concept called cosmic inflation. This theory suggests that in the first fleeting fraction of a second after the Big Bang, the universe did not simply expand. It exploded in growth, inflating from a subatomic speck to a vast cosmic landscape faster than a heartbeat. During this inflationary spasm, space itself stretched at a speed far greater than light, pulling a tiny, homogeneous patch of the early universe and magnifying it into the entire observable cosmos we see today. This is why the distant horizons look the same, because long ago, before inflation, they were neighbors, intimately connected and sharing their properties. Then, in an unimaginable burst of expansion, they were ripped apart and pushed far over their respective light speed horizons. This theory of inflation is a breathtaking fix, a moment when the universe had to break its own initial speed limits to create the uniform conditions we now observe. It paints a picture of a cosmos willing to rewrite its own opening chapter to achieve coherence, a rebellion in its infancy that set the stage for everything to come. Even our own spacecraft began to defy the rules, whispering of a hidden force in the quiet dark of the outer solar system. For decades, the twin probes Pioneer 10 and Pioneer 11 sailed towards the stars, their trajectories tracked with meticulous care. Yet a persistent, nagging mystery followed them. Each spacecraft was experiencing a tiny, unexplained deceleration, a constant, gentle tug back towards the sun so minuscule it was equivalent to the gravitational pull of a single grain of sand. But in the pristine vacuum of space, where the laws of physics are expected to reign with absolute precision, even this infinitesimal drift was a glaring anomaly. It was a ghost in the machine, a force that simply did not belong in any textbook. Scientists were baffled. Was this the first hint of a new physics, a crack in Einstein's theory of gravity itself? Some theorized about the influence of unseen dark matter, or proposed radical modifications to the law of universal gravitation over vast distances. The Pioneer Anomaly became a decades-long obsession, a puzzle that suggested the cosmos might be playing by a different set of rules in the frigid emptiness between the planets. The quest for an answer became a testament to scientific diligence, a painstaking process of elimination that forced researchers to consider every possibility, no matter how exotic or mundane. They meticulously modeled the gravitational pull of every known object in the solar system, from the massive planets to the scattered debris of the Kuiper belt. They scrutinized the spacecraft's own systems, looking for any tiny leak of gas or subtle malfunction that could produce a thrust. For years, the anomaly resisted all conventional explanations, fueling speculation that we were on the verge of a revolutionary discovery. The true answer, however, was hiding in plain sight, a lesson in the subtlety of cause and effect. The breakthrough came not from looking out at the cosmos, but from looking inward at the spacecraft themselves. The Pioneers were powered by radioactive plutonium, and that material generated heat. Engineers realized that this heat was not simply contained, it was radiating away from the spacecraft in the form of infrared light. This thermal radiation, while incredibly weak, was not perfectly symmetrical. A little more heat was radiating from the warm back of the spacecraft's dish antenna than from the front. And in the frictionless void of space, even this tiny imbalance acted like a soft, continuous brake, a gentle photon breeze pushing back against the probe's journey. The mysterious force was not a new law of physics, but the result of an old one, the simple emission of heat, acting in a way no one had fully anticipated. The resolution of the Pioneer Anomaly was a humbling triumph. It demonstrated that the universe often guards its secrets not with grand deceptions, but with subtle, overlooked details. This lesson in careful observation, of searching for the hidden variable in the machine itself, would soon prove vital on a much grander scale, as astronomers turned their gaze to the farthest reaches of the cosmos and discovered a rebellion far more profound than a drifting spacecraft. That subtle drift of the Pioneer probes was a whisper, but the cosmos was about to scream its defiance. The greatest rebellion was not happening in our own solar system, but in the unimaginable depths of intergalactic space. For most of the 20th century, astronomers believed they knew the ultimate fate of the universe. The Big Bang had sent everything flying apart, but the relentless pull of gravity, the combined weight of all the galaxies, was expected to be slowly applying the brakes. The only real question was whether this cosmic deceleration would be enough to one day reverse the expansion, leading to a big crunch, or if the universe would merely coast towards a cold, dark halt. Then, in the late 1990s, two independent teams of researchers made a discovery so shocking it would earn them the Nobel Prize. They were using the most powerful telescopes on Earth to observe a special kind of exploding star, a Type 1, a supernova. These stellar explosions are what astronomers call standard candles. They have a known, predictable brightness. By measuring how dim they appear from Earth, scientists can calculate their distance with incredible accuracy. And by analyzing the color of their light, they can determine how fast they are moving away from us. When these teams looked at the most distant, and therefore the oldest, supernovas, they expected to see the telltale signs of a universe slowing down. The ancient, faraway explosions should have appeared brighter than expected, because if the universe was expanding more quickly in the past, the light would have less distance to travel to reach us today. Instead, they found the opposite. The most distant supernovas were fainter than their models predicted. This meant these ancient stars were farther away than anyone had calculated. There was only one possible and utterly bewildering explanation. The expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, repulsive force was actively pushing galaxies apart, overwhelming the collective gravity of all creation. This force was given a name that perfectly captures our ignorance: dark energy. The implications are staggering. Gravity, the force that shapes planets, stars, and galaxies, the foundational rule of cosmic structure, is not the dominant player in the universe's ultimate story. On the largest scales, a form of anti-gravity is winning. This dark energy now appears to make up about 70% of the entire energy content of the cosmos. We live in a universe where the vacuum of empty space itself seems to possess a latent, repulsive power. This idea is not entirely new. Albert Einstein himself encountered a similar concept when devising his theory of general relativity. His equations showed that a static, unchanging universe was unstable and would collapse under its own gravity. To fix this, he inserted a fudge factor, a repulsive term he called the cosmological constant, to balance everything out. When the universe was later found to be expanding, he called this his greatest blunder. Yet now, it seems Einstein may have been right for the wrong reason. The cosmological constant is the leading candidate for what dark energy could be, a property of space itself that causes it to push outward. Other theories propose dynamic fields, nicknamed quintessence, that change over time. But the core mystery remains. We are forced to accept that nothing, the sheer emptiness between galaxies, is not empty at all. It is the most powerful and prevalent component of reality, a force that dictates the future of everything. The ultimate cosmic rebellion is not a single event, but the very fabric of the stage upon which the drama of the universe plays out, silently pushing the actors apart. This realization forces a humbling question. If we have been so wrong about the nature of nothing, what other fundamental truths are we missing? This quantum entanglement is a rebellion on the smallest possible scale, a direct challenge to the very idea of separate objects. Imagine two electrons born from the same event, twinned in a way that forever links their fates. They fly apart, traveling for years, for light years, to opposite ends of the galaxy. According to all classical rules, they are now independent, but in the quantum world, they are not. Each particle exists in a haze of possibility, its specific properties like spin or polarization not yet determined. It is only when a scientist measures one of them, forcing it to choose a state, say, spinning upward, that its distant twin instantly and definitively snaps into the opposite state, spinning downward. This connection is instantaneous. It happens faster than light could ever travel between them. This is what Albert Einstein, deeply troubled by the implication, famously dismissed as spooky action at a distance. He believed it pointed to a flaw in quantum theory, suggesting that some hidden variables, some unknown mechanism, must be secretly guiding the particles. For decades, it remained a philosophical debate, a ghost in the mathematical machine. Then, in the 1980s, a physicist named Alain Aspect devised a brilliant experiment to settle the argument. His setup was designed to close any possible loopholes. He would measure the properties of entangled particles after they had already separated, changing the settings of his detectors so quickly that no signal, even at the speed of light, could communicate between them. The results were unequivocal. The particles were correlated in a way that defied any explanation based on local hidden variables. They were truly connected in a way that transcended space. This was not a theoretical idea anymore, it was a confirmed fact of nature. So what does this mean for our understanding of reality? It suggests that the universe, at its most fundamental level, is not a collection of isolated islands. It is a deeply interconnected web where separation itself may be an illusion. Information seems to be exchanged, but crucially, not in a way we can use to send a message. We cannot force one particle to spell out a word by manipulating its twin. The universe, in its rebellion, still guards against time travel and paradox. But the spooky action remains, a quiet, constant hum of connection underlying the apparent solitude of every object. From the inexplicable spin of entire galaxies to the instantaneous whisper between two electrons, the cosmos is proving to be far less obedient than we once believed. This deep interconnectedness of the quantum world is one kind of defiance, but the cosmos also hurls physical proof of its rebellion directly at us. Streaking through the atmosphere are cosmic rays, atomic fragments traveling at nearly the speed of light. Most are low energy and common, but a rare few carry an energy so stupendous it defies belief. A single one of these particles can pack the punch of a professionally thrown baseball, all concentrated into a single subatomic speck. This should be impossible, according to a well-established limit in physics named for its discoverers Greisen, Zatsepin, and Kuzmin. Such ultra-high energy particles have a limited range. The universe is not empty, it is filled with the faint afterglow of the Big Bang, the cosmic microwave background. For a proton traveling with such colossal energy, this background radiation is not a gentle glow, it is a thick fog. Each interaction with a microwave photon should act like a brake, sapping the proton's energy until it falls below the theoretical cutoff long before it could ever reach our planet. It is a fundamental speed limit for cosmic travelers, a rule written into the fabric of space itself, and yet our detectors on Earth have recorded them. These outlaw particles are arriving with energies that, by all rights, they should have lost billions of years ago. Their very existence is a direct challenge to our models. Where could they possibly come from? One theory suggests incredibly nearby sources, cosmic accelerators within our local galactic neighborhood that fire them at us before they have time to slow down. But what natural phenomenon could possibly be that powerful? Another, more radical idea is that these particles are a sign of a deeper breakdown. Perhaps Lorentz invariance, the principle from relativity that underpins our entire understanding of space and time, begins to falter at such extreme energies. Maybe the rules of the game are not as rigid as we thought, and at these unimaginable scales, the cosmic speed limit itself is not absolute. Each detection is a data point from the edge of physics, a messenger from the most violent and energetic events in the universe, carrying a simple, humbling message. Our most cherished principles are not the final word. They are merely the best rules we have for a reality that is far wilder and more rebellious than we ever dreamed. Even the faint afterglow of the Big Bang itself holds a secret defiance. After mapping the cosmic microwave background in exquisite detail, scientists expected to see a random, featureless sea of ancient light, the final proof of a perfectly symmetric cosmos. Instead, they found something deeply unsettling. The largest fluctuations in this baby picture of the universe are not scattered randomly across the sky. They appear to be aligned along a particular direction, a mysterious corridor through space that researchers, with a hint of dark humor, nicknamed the axis of evil. This is not a small statistical quirk. It is a correlation of massive features that stretches across the heavens, suggesting the universe might have a preferred orientation, a cosmic north. This discovery directly assaults one of the most sacred principles in all of cosmology, the idea that the universe is homogeneous and isotropic. In simple terms, this means the cosmos should look the same in every direction and have no center or edge on the largest scales. It is the fundamental assumption that allows us to believe we are not in a special place, that the laws of physics are the same everywhere. The axis of evil whispers that this might not be true. Could it be that our entire observable universe is just one patch of a much larger, lopsided cosmos, and we are seeing the shadow of its grander structure? The scientific community has grappled with this anomaly for years. Some argue it is merely a fluke, a statistical ghost in the vast machine of data. Others have meticulously searched for any possible error in the satellite instruments or in the complex data processing that could create such an illusion. Yet the alignment persists. If it is real, the implications are staggering. It would mean the universe has a fundamental handedness, a preferred axis that breaks its ultimate symmetry. This would be a rebellion not just of matter or energy, but of space-time itself, forcing us to rewrite the first page of our cosmic story and question whether we are truly seeing the universe as it is, or merely our small, skewed corner of a far stranger reality. This ultimate defiance reaches its peak not in the vastness of space, but in the absolute darkness of a black hole. Here, two of our most successful descriptions of reality, general relativity and quantum mechanics, wage a silent war. According to Einstein's theory, a black hole is defined only by its mass, spin, and charge. If you throw a grand piano, a library of books, or a million diamonds into one, the black hole would not care. It would simply grow heavier, its event horizon expanding slightly, but all the unique information about what fell in, the intricate arrangement of matter that made a piano, would be utterly and permanently erased from our universe. This is a complete violation of a sacred rule in quantum mechanics, which states that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. This is the black hole information paradox, a fundamental clash at the edge of known physics. The crisis was sharpened by Stephen Hawking's revolutionary work. He realized that black holes are not completely black. Due to weird quantum fluctuations at the very boundary of the event horizon, pairs of virtual particles can pop into existence. Normally, these particles annihilate each other instantly, but at the precipice of a black hole, one particle can fall in while the other escapes, stealing a tiny amount of the black hole's energy and radiating it away into space. This is Hawking radiation, a faint glow that causes the black hole to slowly evaporate over eons. And here lies the terrible paradox. The radiation Hawking described is purely thermal, a featureless hiss containing no information about what fell in. So when the black hole finally evaporates completely, all the information about the piano, the books, and the diamonds is gone forever. The universe has forgotten. Physicists have been grappling with this for decades, and their proposed solutions are as strange as the problem itself. One leading idea is the Holographic Principle, which suggests that all the information about what falls into a black hole is not lost inside, but is somehow encoded on its two-dimensional surface, the event horizon, like a cosmic fingerprint. The three-dimensional interior we imagine is just a projection of that data. Another, more violent solution is the firewall hypothesis. It proposes that the event horizon is not a smooth gateway, but a blazing wall of high-energy particles that would instantly incinerate anything crossing it, preserving information by never letting it truly enter in the first place. This is not a rebellion we can see with a telescope. It is a battle of logic and mathematics, a screaming contradiction between the rules of the very large and the very small, revealing that our universe's own instruction manual is torn right down the middle. Even the very expansion of the cosmos, a number we thought we were close to pinning down, is now a battlefield. The Hubble constant, the rate at which the universe is stretching, can be measured in two ways. We can look back to the infant universe, to the pristine snapshot of the cosmic microwave background taken by the Planck satellite. This ancient light gives us a reading of the expansion rate from the very beginning. Or we can use modern markers like those distant supernovas and pulsing stars called Cepheids to measure how fast the nearby universe is flying apart today. Both methods are incredibly precise, honed by decades of scientific work, yet they do not agree. The universe today is expanding faster than the early universe says it should be. This is the Hubble Tension, a stubborn discrepancy that has only grown with better data. It is like carefully calculating how much fuel you need for a long journey, only to find your car is mysteriously burning through it faster than any formula can explain. For cosmologists, this is a 5-alarm fire. It suggests a fundamental flaw in our standard model of cosmology, the lambda CDM model, which has been the bedrock of our understanding for a generation. This model, which elegantly combines dark energy and cold dark matter, successfully predicts the large-scale structure of the cosmos and the properties of the ancient afterglow. But it cannot make the early and late expansion rates match. The tension points to something missing, a crack in the foundation of modern physics. What could be causing this cosmic rift? Theorists are scrambling for answers, proposing exotic new ingredients for our cosmic recipe. Perhaps a form of early dark energy briefly surged and altered the primordial universe before fading away. Maybe dark matter is not completely cold and stable, but has properties that allow it to interact with itself or decay over time. Or the solution could lie in the ghostly neutrino, a particle we once thought was massless. If neutrinos have unexpected masses or come in new, sterile varieties, they could have subtly changed the rate at which structures formed, throwing off our cosmic calculations. This is not an abstract debate. It is an active rebellion happening in the data itself, a direct challenge to our most cherished model of the cosmos. The fate of our entire standard model of cosmology now hangs in the balance, forcing us to wonder what other invisible actors are still waiting in the wings, quietly directing the show. The quietest force in the universe is also the most baffling. While the quantum world is a storm of electromagnetic pushes and pulls, and atomic nuclei are bound by a powerful nuclear glue, gravity barely registers on the subatomic stage. The force that holds entire galaxies together is so weak that a simple refrigerator magnet can defy the gravitational pull of our entire planet, effortlessly lifting a paperclip into the air. This is not a minor difference, it is a cosmic chasm of staggering proportions. Physicists call this the gauge hierarchy problem, and it asks a simple, profound question: why is gravity so unimaginably feeble? The numbers are almost impossible to grasp. The the force of gravity is roughly 10 to the power of 36 times weaker than the electromagnetic force. To put that in perspective, that number is a 1 followed by 36 zeros. It is the difference between the weight of a single bacterium and the combined mass of every star in the observable universe. This is not just a quirk of nature, it is an absurd, unnatural fine-tuning that the standard model of particle physics cannot explain. It is as if the cosmic rulebook contains a single, wildly out-of-place sentence written in a font a trillion times smaller than all the others. The problem runs even deeper because this weakness is directly tied to the Higgs field, the invisible energy field that gives particles their mass. The stability of this field, and by extension the stability of all matter, depends on a precise and incredibly delicate cancellation of quantum effects. Without this seemingly miraculous fine-tuning, the Higgs field would have collapsed the universe in a flash shortly after the Big Bang. Why does the universe exist in this incredibly precarious yet perfectly balanced state? The search for an answer has led physicists to propose realities stranger than fiction. One leading idea is supersymmetry, a theory that posits every known particle has a hidden, super-heavy twin partner. These shadow particles would provide a natural, elegant cancellation effect, stabilizing the Higgs field and making gravity's extreme weakness a logical outcome of a deeper symmetry. The only problem is that after decades of searching with the most powerful particle colliders on Earth, we have found no evidence these superpartners exist. Another, even more mind-bending solution involves the very fabric of space. What if gravity only seems weak because it is not confined to our three-dimensional reality like the other forces? The theory of extra dimensions suggests that gravity is actually as strong as the other forces, but its influence is diluted as it leaks out into unseen, compact dimensions curled up at every point in space. We are only feeling a tiny, feeble shadow of its true strength. This rebellion of the weak force is a quiet one, but its implications are deafening. It tells us that our understanding of the most fundamental layers of reality is not just incomplete, it may be fundamentally misguided, pointing toward a hidden architecture to the cosmos that we have only just begun to suspect. Even the most perfect image of the infant universe contains a strange, cold blemish. In the detailed maps of the cosmic microwave background, one region stands out not for its heat, but for its profound chill. This is the CMB Cold Spot, a vast and unusually cold patch of sky so large it defies easy explanation. It is as if you found a single, freezing cold continent on an otherwise warm and uniform globe. One compelling theory suggests this spot is a shadow cast by a cosmic supervoid, an immense region of space that is startlingly empty. If light must climb out of such a deep gravitational well on its journey to us, it loses energy, stretching its wavelength and cooling down in a process known as the integrated Sachs-Wolf effect. Think of a cyclist exhausted after pedaling up a long, gradual hill, arriving with less energy than they started with. The light from the cosmic microwave background, passing through a supervoid, would arrive in exactly this way, cooler and more tired. Yet the sheer scale of the required void is the problem. To create a cold spot this size and this cold, the underdense region would need to be unimaginably vast, perhaps 1 billion light-years across, and profoundly empty. Finding such a colossal nothingness in a universe woven together by the gravitational web of dark matter is in itself a major cosmic puzzle. Could the cosmos really contain a void so grand it leaves a chill on the edge of creation? If this is the answer, it points to a level of large-scale structure so extreme it challenges our models of how the universe evolved. But what if the void is not the cause, but merely a coincidence? The plot thickens when we consider that even the most powerful telescopes have struggled to find a supervoid large enough to explain the cold spot's pronounced chill. This gap in the evidence opens the door to far more exotic possibilities. Perhaps the cold spot is not a shadow at all, but a scar. One radical theory proposes it could be evidence of a cosmic texture, a flaw in the fabric of space-time itself. In the early universe, as the fundamental forces of nature were settling into their current states, the cosmic material might have cooled unevenly, creating tangled knots of energy like cracks forming in ice. If one of these primordial defects, a texture, were to unravel, it would release a tremendous burst of energy that could imprint a cold spot on the cosmic microwave background. This would be a fossil from the universe's most turbulent infancy, a relic of a phase transition that forever altered the properties of reality. An even more staggering hypothesis suggests the cold spot could be a bruise, the imprint of a collision with another universe. In the multiverse scenario, our universe is one bubble in a frothing cosmic sea. The immense energy released if our bubble had gently bumped into another during its initial inflation could have left a permanent anisotropic mark on our sky, a cosmic fingerprint from a reality beyond our own. Each of these ideas, from the rare statistical fluke to the cosmic texture or the multiverse collision, represents a profound rebellion. The cold spot challenges the cherished cosmological principle that the universe is uniform on the largest scales. It hints that our cosmic neighborhood might be exceptional in ways we are only beginning to grasp, a single cold patch whispering that the grandest structures and most dramatic events may be written in the faintest chill of the ancient light. Even the first few minutes of the universe, a time we thought we understood, hold a stubborn, elemental mystery. In the seething heat of the newborn cosmos, just moments after the Big Bang, nuclear fusion forged the first light elements in a process called Big Bang nucleosynthesis. For the most part, this primordial recipe is a spectacular success. The predicted amounts of hydrogen and helium match almost perfectly with what we observe throughout the universe. But there is one glaring exception, one ingredient that refuses to fit. The theory predicts that a specific, tiny amount of the element lithium-7 should have been created and scattered across the cosmos. Yet when we look at the oldest stars in our galaxy, which formed from that pristine primordial material, they consistently show only about a third of the lithium that should be there. This is the lithium problem, a deficit that has persisted for decades, a quiet but persistent rebellion in the foundational story of creation. So where did the lithium go? The nuclear reactions in that first cosmic forge are exquisitely balanced. Protons and neutrons fuse to form deuterium, then helium, and a tiny trace of lithium-7. The calculations are precise, and they work for everything else. This forces us to confront a radical possibility. Perhaps our understanding of the nuclear physics itself is incomplete. Could there be an unknown nuclear reaction pathway that destroyed the lithium as quickly as it formed? Or maybe an exotic particle, something not in the standard model, was present in those early moments, interacting with the primordial soup and subtly altering the outcome. Another possibility points not to the beginning, but to the end. What if the lithium was created in the right amount, but something is systematically destroying it in the ancient stars we use as cosmic probes? These old stars act like deep freeze time capsules, preserving the composition of the early universe, but their interiors are violent, churning places. Could complex stellar processes we do not fully understand be slowly mixing the lithium down into the stellar cores, where fierce temperatures burn it away? Each potential solution opens a new can of worms. Invoking new physics challenges the bedrock of cosmology, while blaming the stars demands we rethink our models of stellar evolution. This is not just a debate about a single element. Lithium is a crucial clue. Its absence is a data point from the universe's first 3 minutes, telling us that our otherwise perfect story of the beginning is missing a vital page. It is a rebellion written in the very atoms that make up the cosmos, a whisper from the dawn of time that our model, for all its glory, is not yet complete. Our most embarrassing failure is not about what we see, but about what we calculate. The energy hidden in the vacuum of space itself, a concept known as zero-point energy, presents a problem of such staggering proportions it is often called the vacuum catastrophe. According to the well-tested rules of quantum field theory, empty space is not empty at all. It is a seething, bubbling foam where virtual particles constantly flicker in and out of existence. When physicists calculate the combined energy of this endless quantum frenzy, the number they get is beyond astronomical. It suggests that every single cubic centimeter of nothingness should be packed with more power than all the energy in the known universe. This is the theoretical prediction. Now compare this to the observed reality. We can measure the energy of the vacuum indirectly by watching how it pushes the universe apart, the same dark energy driving the cosmic acceleration. The value we get from these observations is not just a little bit smaller than the prediction. It is smaller by a factor of 1 followed by 120 zeros. To grasp the sheer absurdity of this mismatch, imagine predicting that a single grain of sand would weigh more than the entire observable universe. Our best theory and our direct measurements of reality are not even in the same galaxy of agreement. This is not a small rounding error, it is a screaming contradiction. The vacuum catastrophe suggests that either our understanding of the quantum vacuum is fundamentally wrong, or that some miraculous, perfect cancellation is happening that we cannot explain. It forces us to confront the terrifying possibility that we are missing a core principle of physics, one that unites the quantum world with the force of gravity. The resolution to this rebellion will likely require a theory of quantum gravity, a framework that has eluded the greatest minds for a century. This is the ultimate humiliation, a reminder that the very nothingness surrounding us holds the greatest unsolved mystery of all. Deep within the heart of a precision machine, a tiny, unstable particle is whispering of a world beyond our own. This is the muon, a heavier, short-lived cousin of the electron, and its most recent measurement has sent a jolt through the world of fundamental physics. The focus is on its magnetic moment, a technical term for how strongly it behaves like a tiny magnet. Imagine a perfectly balanced top spinning in a vacuum, its axis wobbling with a predictable, steady rhythm. According to the immensely successful standard model of particle physics, which catalogs all known particles and forces, the muon's wobble should be precisely calculable. Yet in a landmark experiment at the Fermilab Particle Accelerator, scientists have found that the muon's spin wobbles just a little bit faster than the theory says it should. The discrepancy is minuscule, a difference of about 2 parts in 1 billion, but in the hyper-precise world of particle physics, it is a screaming anomaly. Why is this so significant? The muon is an exceptional probe because it is unstable, living for only 2/millionths of a second, and in that fleeting existence, it is far more sensitive to the invisible quantum foam that fills empty space. As it spins, it is constantly buffeted by a sea of virtual particles flickering in and out of existence. The standard model accounts for the known particles in this sea, but if there are unknown particles or forces at play, they would give the muon spin an extra, imperceptible nudge. This tiny wobble, this faint tremor in its rotation, could be the first tangible evidence of something entirely new. The most exciting possibility is that this anomaly points to supersymmetry, a theorized framework where every known particle has a massive, hidden superpartner. These shadow particles could be the very presence tweaking the muon's magnetic moment, and could also solve other deep puzzles like the unnatural weakness of gravity. Other theories suggest new, hidden forces or dimensions. This rebellion is not happening in a distant galaxy or in the early universe, but in a controlled laboratory experiment, a crack in the foundation of our most complete theory of matter and energy. The humble muon, a speck of existence that vanishes in an instant, may be holding the key to the next great revolution in our understanding of reality. Our own star holds a secret contradiction deep within its past. The sun, the steady engine of our solar system, has not always shone with its present strength. Models of stellar evolution, the very same rules that let us understand the life cycles of distant suns, tell us that billions of years ago our sun was a much dimmer star, perhaps 30% fainter than it is today. With that much less energy reaching our young planet, the Earth should have been a global snowball, a frozen world locked in a deep and permanent ice age. Yet the geological record tells a completely different story. Ancient rocks from that very period show clear signs of flowing liquid water, and fossil evidence suggests life may have already begun its intricate dance. This is the faint young sun paradox, a climate puzzle written in stone that challenges the consistency of our cosmic models. How could a world warmed by a weaker sun avoid becoming a permanent icehouse? The most compelling solution points to an alien sky, an atmosphere nothing like the one we breathe today. In its youth, Earth's air may have been thick with potent greenhouse gases like methane and ammonia, creating an insulating blanket far more effective than our current carbon dioxide. This dense, primordial haze could have trapped enough of the sun's feeble heat to keep the oceans liquid and the planet habitable. Another theory suggests the young Earth itself was darker, with less reflective land surface and more ocean, absorbing a greater percentage of the precious sunlight that did arrive. This rebellion is not a clash of fundamental particles or cosmic forces, but a deep inconsistency in our own backyard. It reveals that our understanding of stellar life cycles and planetary evolution can contain profound, unresolved conflicts. The faint young sun paradox connects the rules of stellar physics directly to the possibility of life, forcing us to ask if our planet's warm beginnings were a happy atmospheric accident or a necessary condition written into the laws of cosmic chemistry. Our very place in the cosmos might be an exception to the rule. For generations, a cornerstone principle of cosmology has been that the universe is largely uniform, that on the grandest scales, no place is truly special. This cosmological principle assures us that our view from Earth is an average one, allowing us to extrapolate what we see locally to the entire cosmos. Yet, mounting evidence suggests we may be living in a cosmic hole, a vast and startling emptiness known as the KBC Void. This is not a small pocket of space, but a staggering spherical underdensity, a bubble of nothingness nearly 2 billion light-years across, with our Milky Way galaxy sitting uncomfortably close to its center. Within this void, the density of galaxies, clusters, and matter is significantly lower than the predicted cosmic average. We are, it seems, residing in one of the universe's grandest deserts. The existence of such a colossal void directly challenges the cosmological principle. How could the universe be smooth and uniform if we are sitting inside a bubble of such extreme emptiness? The implications ripple outward, touching some of the most pressing mysteries in modern astronomy. The measured expansion rate of the universe, the Hubble constant, is derived from observing nearby galaxies. But if those galaxies are all inside this local void, their motions are not representative of the true global expansion. Think of it like measuring the flow of a river while standing in a massive, slow-moving eddy. your local measurements would not reflect the true, powerful current of the main channel. In the same way, the strange pull of this cosmic nothingness could be distorting our measurements of both the Hubble constant and the strength of dark energy, potentially explaining why our local and early universe measurements do not agree. The debate is fierce. Is the KBC Void a real structure, or is it a statistical fluke, a trick of incomplete data? If it is real, then our cosmic address is not average at all. We are not in a typical suburban neighborhood of the universe. We are in a uniquely sparse and quiet corner. This forces a profound reconsideration of everything we think we know. The light from distant supernovas, the distribution of galaxies, the very acceleration of space itself, all of it must be reanalyzed through the lens of this potential void. We are forced to ask a humbling question: are the fundamental forces and constants we measure truly universal, or are they merely local bylaws specific to our strangely empty patch of the cosmos? The very concept of time, the steady rhythm that orders our lives, is a lie, or at the very least, it is a profound illusion, a rebellion playing out in the foundational language of physics itself. Our two most powerful descriptions of reality, general relativity and quantum mechanics, are locked in a silent war over the nature of time, and this conflict is the single greatest obstacle to a complete theory of everything. In Einstein's universe, time is not a rigid backdrop. It is a dynamic, pliable dimension, deeply interwoven with the three dimensions of space into a single fabric called space-time. This fabric can be stretched, warped, and curved by mass and energy. In this view, time is relative. It can slow down or speed up depending on gravity and velocity. There is no universal clock ticking for everyone everywhere, but in the quantum world, the rules are utterly different. For the equations of quantum mechanics to work, time must be an external, absolute, and unchanging parameter. It is the steady, relentless metronome against which the frantic dance of particles is measured. It simply exists outside the system, providing a fixed stage for the quantum weirdness to play out. This is the problem of time. The same word describes two completely different, fundamentally incompatible concepts. It is as if one rulebook describes a river, a flowing, changing entity that shapes the landscape, while the other describes a stopwatch, a perfect, immutable tool for measurement. How can you possibly combine a river and a stopwatch into a single, coherent picture? This conceptual schism has forced physicists to propose radical solutions. One path is loop quantum gravity, which attempts to quantize space-time itself. In this theory, space and time are not smooth and continuous, but are made of tiny, discrete loops, a fabric woven from a billion individual threads. In this framework, time itself might emerge from the relationships between these fundamental units, losing its independent existence. Another approach, string theory, suggests that the fundamental ingredients of reality are not point-like particles, but unimaginably small, vibrating strings. To make the mathematics of string theory work consistently, it requires more than the three spatial dimensions and one time dimension we experience. It posits the existence of extra, hidden dimensions, all curled up at every point in space. In some interpretations of string theory, time itself could be an emergent property arising from the complex vibrations within this higher dimensional arena. These are not just abstract ideas, they are desperate attempts to heal a fracture at the heart of physics. The problem of time is a rebellion that strikes deeper than any galaxy spinning too fast or any particle with too much energy. It is a crisis of meaning. It suggests that our most intuitive experience, the steady, forward march of time, might be a shadow, a collective illusion generated by a deeper, timeless reality. We are trying to read the universe's ultimate rulebook, only to find that the most fundamental word on the first page, the word time, is written in a language we have not yet learned to speak. Even the silent, dark spaces between stars can suddenly scream with a violence that defies all expectation. Fast radio bursts are one of the most electrifying mysteries in modern astronomy, incredibly powerful flashes of radio energy that last for less than the blink of an eye. They travel across billions of light-years of space, carrying more energy in a single millisecond than our Sun releases in 80 years, and then they vanish without a trace. The first one was discovered in 2007, buried in archived data from a radio telescope in Australia, a spike of energy so intense and so brief that astronomers initially doubted it was real. Was it a glitch, a piece of terrestrial interference, or something else entirely? As more telescopes were trained on the sky, more of these bursts were found, confirming a terrifying new reality. The cosmos is punctuated by these sudden, inexplicable explosions, and we have no idea what is causing most of them. The hunt for their origin became a cosmic detective story of the highest order. The first major breakthrough came when astronomers caught one in the act of repeating. Unlike the single, cataclysmic explosions they had seen before, this source, named FRB 121102, fired off multiple bursts over time. This single observation ruled out any source that destroys itself in the process, like the collision and merger of two ultra-dense neutron stars. The repeater had to be an object that could survive its own violent outburst, something like a magnetar. Magnetars are a special type of neutron star, the collapsed core of a giant star, possessing magnetic fields so powerful they could strip the information from every credit card on Earth from halfway across the galaxy. It was a compelling suspect, and in 2020, the theory was spectacularly confirmed when a known magnetar within our own Milky Way galaxy erupted, producing a fast radio burst. Finally, we had a culprit we could point to, but the case was far from closed. While some bursts are now linked to these magnetic monsters, the repeating bursts from deep space continue to defy easy explanation. Their patterns are strange and unpredictable, sometimes firing off in frantic succession and then falling silent for years. The energies involved are so immense that they strain our models of what even a magnetar is capable of producing. This has forced scientists to consider even more exotic possibilities. Could they be produced by the violent tantrums of young, hyperactive magnetars? Or perhaps they are the death throes of evaporating black holes, theoretical objects proposed by Stephen Hawking. The sheer power and brevity of the signals have, inevitably, led to more speculative ideas, including the possibility of advanced alien civilizations harnessing unimaginable energies for interstellar communication or propulsion. While this is the least likely explanation, its continued discussion highlights just how thoroughly these bursts break our existing models of high-energy astrophysics. Fast radio bursts are a different kind of cosmic rebellion. They are not a slow, persistent anomaly like the expansion of the universe, but a sudden, violent shattering of the quiet. They remind us that the cosmos is not a static museum, but a dynamic, often violent arena where new and unpredictable phenomena can erupt without warning, challenging our understanding and ensuring that the final chapter of physics is far from written. Even the weight of a ghost can shake the foundations of physics. Deep within the data of a particle collider, scientists measured the mass of a crucial but fleeting particle, the W boson. This is not a stable piece of matter, but a ghostly force carrier, the particle responsible for the weak nuclear force that drives radioactive decay and initiates the nuclear fusion that powers the sun. It is a fundamental cornerstone of the Standard Model, our most precise catalog of the particles and forces that build reality. For decades, the predicted mass of this particle was a triumph of theoretical physics, a number calculated with such exquisite precision it was like predicting the exact weight of a single snowflake in a blizzard. The entire model is a delicate, interlocking web, and the mass of the W boson is tied directly to the masses of other particles, like the top quark and the famous Higgs boson. The system was a perfect, self-consistent clockwork. Then came the new data from the CDF experiment at Fermilab. After a decade of painstaking analysis, the collaboration announced a result that sent a jolt through the global physics community. Their measurement showed the W boson's mass was significantly heavier than the standard model's elegant prediction. The discrepancy was tiny, a mere fraction of a percent, but in this hyper-precise realm, it was a screaming siren. It was as if you had calculated the exact dimensions of a key to fit a lock, only to find the real key was just a little bit too large, proving the lock's mechanism was more complex than you ever imagined. This anomaly pointed directly to the existence of unknown particles or forces, subtle influences that would tweak the W boson's properties in just this way. For a thrilling moment, it seemed we had our first undeniable crack in the standard model's formidable armor, a direct sign of the new physics that theorists have been chasing for 50 years. The excitement, however, was soon tempered by reality. Other experiments, including those at the Large Hadron Collider, have since reported measurements that are much closer to the original standard model prediction, clouding the picture with uncertainty. The initial shockwave has settled into a persistent, nagging question. Was the CDF result a statistical fluke, a masterpiece of measurement error, or is it the first faint signal of a deeper truth, a rebellion waiting for clearer data to confirm it? This episode, even without a definitive conclusion, is a powerful lesson in the scientific process. It shows how the relentless pursuit of precision, the act of measuring the universe with ever finer rulers, can reveal the subtlest of cracks in our most successful theories. The hunt for the true mass of the W boson continues, a quiet but intense battle of data against data, keeping the door wide open for a revolution to emerge from the heart of particle physics itself. This profound silence from the stars is a rebellion against our deepest hopes. We gaze at a galaxy filled with hundreds of billions of suns, most likely orbited by countless Earth-like worlds, a cosmic tableau that seems custom-made for life to flourish. The numbers alone suggest a universe teeming with civilizations, a crowded interstellar community, and yet when we listen, we are met with an unnerving, absolute quiet. This contradiction is the Fermi Paradox, a puzzle that asks a simple, haunting question: where is everybody? One chilling answer is known as the Great Filter. This hypothesis suggests that the evolution of life from its basic origins to a spacefaring, technologically advanced civilization is not a smooth, inevitable path. Instead, it is an obstacle course littered with traps, and there exists one particular step, one evolutionary or technological barrier, that is almost impossible to overcome. This is the Great Filter, a cosmic bottleneck that ruthlessly prunes the tree of intelligent life. The terrifying implication of this idea hinges on a single, urgent unknown. Is the Great Filter located in our past, or is it waiting for us in our future? If the filter is behind us, it means that one of the steps we have already passed was the incredibly difficult one. Perhaps the spontaneous genesis of life from non-living chemistry is a miracle of such astronomical improbability that Earth is a singular aberration. Or maybe the leap from simple prokaryotic cells to complex eukaryotic life, a transition that took over 1 billion years on our planet, is the true bottleneck. In this scenario, we are not just lucky, we are cosmic unicorns, the first and possibly only species in our entire galactic neighborhood to have made it this far. The silence is then a testament to our profound rarity. The alternative is far more frightening. What if the filter is still ahead of us? In this version of the story, the development of technology and intelligence is not the pinnacle of evolution, but its death sentence. The filter could be an inherent self-destruction mechanism that triggers upon reaching a certain level of technological prowess. It might be the invention of nuclear weapons and the ever-present threat of global annihilation. It could be the unintended consequences of a runaway artificial intelligence. Or perhaps it is something we have not even conceived of yet, a technological pitfall that every advanced culture inevitably stumbles into, silencing them before they can ever hope to reach the stars. The eerie quiet would then be a graveyard, a warning from a universe where intelligence is a fleeting, self-extinguishing flame. This connects the cosmic rules of physics and chemistry directly to the potential laws of biology and sociology. The development of life and consciousness may not be a gentle, guided process, but a brutal gauntlet governed by restrictions far more severe than we have ever assumed. The silence is not empty, it is loud with implication. It is a rebellion against our narrative of progress, forcing us to confront a terrifying possibility that the ultimate rule for intelligent life is not to spread across the galaxy, but to vanish without a trace. Einstein could never accept the ghostly connection of entangled particles. Along with his colleagues Podolsky and Rosen, he formulated a brilliant thought experiment designed to prove that quantum mechanics was an incomplete theory, a temporary description hiding a deeper, more sensible reality. Their argument, known as the EPR Paradox, was a masterstroke. It presented a scenario with two entangled particles flying apart. Quantum mechanics stated that until you measured one, its properties like position or spin were not just unknown, but genuinely undefined. The act of measurement itself forced the particle to choose a state, and its twin would instantly assume the corresponding state, no matter the distance. Einstein argued this was absurd. He believed in local realism, the bedrock principle that objects are only influenced by their immediate surroundings, and that no signal can travel faster than light. The instantaneous correlation, he insisted, meant that the particles must have carried hidden instructions with them from the moment they parted ways. The spooky action was just an illusion, proof that quantum theory was missing these hidden variables. For decades, this remained a philosophical debate, a clash of worldviews. Then came the experiments. Physicists like John Bell devised a way to test it, and Elaine Aspect built the apparatus. They set up detectors to measure the particles' properties after they were too far apart to communicate, even at light speed. The results were unequivocal. The quantum predictions were correct, and Einstein's hidden variables were ruled out. The particles were connected in a way that transcended space. This confirmation of non-locality was a profound shock. It means the universe is not locally real in the way we experience everyday life. Two objects can be so deeply linked that what happens to one immediately influences the other, even if an entire galaxy lies between them. Your coffee mug sitting on the desk seems separate and independent, but at the fundamental quantum level, the concept of true separation begins to blur. This is a rebellion against the very idea of isolated things, suggesting the cosmos is woven together with invisible threads of instantaneous connection, a hidden wholeness underlying the apparent solitude of existence. The heart of our own galaxy is screaming with a light we cannot explain. For years, telescopes designed to scan the sky for the most energetic form of light, gamma rays, have been trained on the dense, chaotic core of the Milky Way. They expected to see a predictable mix of sources, the usual suspects like spinning neutron stars known as pulsars, or the remnants of ancient supernova explosions. But the data revealed something more, an unexpected and persistent glow of gamma rays emanating from the galactic center. This is the galactic center excess, a mysterious surplus of energy that has no clear conventional origin. It is as if you were listening to a symphony and heard one instrument playing a note far louder than the score dictated, a note that does not belong to any known instrument in the orchestra. The most tantalizing explanation for this strange signal involves the very ghost we have been chasing, dark matter. The theory is as elegant as it is profound. If dark matter is made of theoretical particles such as WIMP or weakly interacting massive particles, then they could be their own antimatter counterparts. When two of these particles collide, they would annihilate each other in a flash of pure energy, producing the very gamma rays we are detecting. The center of a galaxy, with its immense gravitational pull and dense concentration of matter, would be the perfect place for these rare but constant annihilations to occur. This excess glow could be the first direct signal of dark matter particles destroying themselves, a faint but definitive signature of the universe's most elusive substance. Yet science demands caution, and a fierce debate has erupted. Could this excess simply be a dense crowd of unresolved pulsars, too faint for our current telescopes to distinguish individually? Or is it the product of a recent burst of star formation, creating a population of powerful but short-lived stellar objects? Each possibility has its champions, and the battle over the data is a masterclass in scientific skepticism. The resolution of this rebellion, happening right in our cosmic backyard, carries immense weight. If the dark matter interpretation proves correct, it would be a landmark achievement, finally giving a face and a name to the invisible scaffolding of the cosmos. It would transition dark matter from a gravitational ghost to a tangible particle with specific properties and behaviors. But if a more mundane astrophysical source is to blame, it forces us to admit that even the center of our own home galaxy still holds profound mysteries about the ordinary, yet violent processes of stellar life and death. Either way, the galactic center excess is a stark reminder that the most fundamental answers may be hiding in the last place we would think to look, the brilliant, tumultuous heart of our own Milky Way. The very engine of our reality runs on a one-way street. You can mix cream into coffee, but you can never unmix it. A shattered glass does not spontaneously reassemble itself on the floor. This relentless forward march is the arrow of time, and it is the most fundamental rule of our everyday existence. Strangely, the underlying laws of physics do not seem to care about this direction. If you watch a film of two electrons colliding and bouncing apart, and then you play that film in reverse, both sequences look perfectly valid according to the equations. The same is true for gravity and electromagnetism. These laws are time-symmetric. They work just as well running backwards as they do forwards. So why does our universe so clearly prefer one direction? The answer lies in a concept called entropy, which is essentially a measure of disorder or randomness. The second law of thermodynamics states that the total entropy of a closed system always increases over time. Things move from order to disorder, from concentration to diffusion, from a state of low probability to a state of high probability. This is why your tidy room inevitably becomes messy without effort, and why heat always flows from a hot object to a cold one, never the reverse. The entire universe is that ultimate closed system, and its entropy is constantly increasing. This gives us our powerful, undeniable arrow of time. But this raises a profound question. If entropy always increases, then it must have been even lower in the past. This line of reasoning points directly back to the very beginning, to the Big Bang. For the arrow of time to exist at all, the universe must have started in a state of incredibly, almost impossibly low entropy. It was a state of exquisite order and uniformity, a perfectly smooth and dense soup of energy. From that singular, ordered beginning, the only possible direction was outward, toward the higher entropy states of stars, galaxies, and the complex, messy cosmos we see today. This is a subtle but profound cosmic rebellion. The universe did not break a physical law, but it broke the symmetry of those laws. Out of all the possible starting conditions, it chose one that gave time a distinct and irreversible direction. The cosmic egg did not just hatch, it exploded into a future of ever-increasing chaos and complexity. This initial low-entropy state is the reason we remember the past but not the future. It is the reason cause always precedes effect. Without this single, special starting point, time would have no meaning, and causality would dissolve into a fog of random events. The forward flow of time is not just a human perception. It is a direct inheritance from the universe's first moment, a cosmic directive written into the fabric of existence that guides everything from the decay of an atom to the ultimate fate of all galaxies. Far beyond the familiar orbits of Neptune and Pluto, in the deep freeze of the Kuiper Belt, a handful of icy worlds are tracing paths that make no sense. Their elongated orbits are mysteriously clustered, tilted in a way that suggests they are all being herded by an unseen shepherd. The mathematics of gravity points to a single, staggering conclusion: a hidden planet, perhaps 10 times the mass of Earth, silently carving its path through the outer darkness. This hypothetical world, known as Planet 9, would be a true cosmic rebel, a giant that has evaded our gaze while fundamentally shaping a distant part of our own solar system. The evidence comes from the peculiar orbits of a group of extreme trans-Neptunian objects. These frozen relics do not wander randomly. Instead, their orbits are aligned, their points of closest approach to the Sun bundled together as if an invisible hand is guiding them. The odds of this happening by pure chance are astronomically low. A planet of this size would exert a profound gravitational influence, its immense pull sculpting the paths of these smaller bodies over billions of years. To explain the observed clustering, this world would need a wildly elliptical orbit, swinging from a perihelion perhaps 300 times farther from the Sun than Earth, out to an aphelion over 600 times that distance. A single year on Planet 9 could last 20,000 Earth years, a slow, silent procession in the Sun's backyard. The hunt for this ghost world is one of astronomy's great modern quests. Teams are using the world's most powerful telescopes, from Subaru in Hawaii to the Vera Rubin Observatory being built in Chile, to scan the vast celestial haystack for this single, faint needle. The challenge is immense, as the planet would reflect very little sunlight, appearing as a dim speck of cold infrared glow against an already black canvas. Its motion would be agonizingly slow, requiring painstaking comparisons of sky images taken weeks or months apart to detect any movement. This potential discovery within our own solar system is a humbling reminder of how much we have left to learn. For centuries, we have mapped our celestial neighborhood, believing we had cataloged its major players. The possibility of a planet larger than Earth still hiding in the shadows proves that our own cosmic backyard can hold monumental secrets, a rebellion of omission that challenges the very completeness of our solar system's portrait. Deep within the heart of the atom, a different kind of rebellion brews, one of perfect balance where chaos was expected. The rules governing the nuclear force that binds protons and neutrons together, known as quantum chromodynamics, contain a strange and silent loophole. The mathematics allow for a parameter, a single dial that, if turned even slightly away from zero, would make the universe look profoundly different. This dial is connected to a fundamental symmetry known as CP. CP stands for the combined operations of charge conjugation, which swaps particles with their antimatter counterparts, and parity, which mirrors space as if reflecting it in a perfect looking glass. For most interactions, this CP symmetry is respected. The universe treats a process and its mirrored antimatter version the same way. But in the weak nuclear force, this symmetry is dramatically broken. A world made of antimatter would not behave exactly like our own. Given this violation elsewhere, physicists fully expected to find a similar CP violation in the strong nuclear force. This would manifest in a very specific way. It would give the neutron, a neutral particle at the heart of every atom, a slight lopsidedness. It would possess what is called a permanent electric dipole moment, meaning it would have a positive charge on one end and a negative charge on the other, like a tiny subatomic bar magnet. The theory permits this, and given the broken symmetry elsewhere, it should be there. Yet, when scientists measure the neutron with incredible precision, they find nothing. The electric dipole moment is zero to an astonishing degree of accuracy. This is the strong CP problem, a puzzle of missing asymmetry. Why is the strong force so perfectly symmetrical when its sibling force is not? The universe had a chance to be messy, to be lopsided on a fundamental level, and it inexplicably chose perfect balance. This quiet perfection is itself a rebellion, a defiance of our expectations. The most elegant solution to this mystery introduces a ghost, a new particle called the action. The action is a hypothetical entity that acts as a cosmic correction factor, a field that dynamically adjusts to keep that troublesome dial set perfectly to zero. It is a guardian of symmetry, whispering through the quantum fields to ensure the neutron remains perfectly round. The profound consequence is that this action, born to solve an arcane problem in nuclear physics, turns out to be a perfect candidate for the universe's missing mass, dark matter. Billions of these invisible particles could be flowing through you every second, their collective gravity holding galaxies together, all because of a hidden symmetry in the strong nuclear force. The search for the action is a direct hunt for this cosmic peacemaker, a particle that fine-tunes the universe in a way we are only beginning to grasp. A single radio signal screamed into the void and was gone. On a hot August night in 1977, an astronomer named Jerry Amon was reviewing data from the Big Ear radio telescope at Ohio State University. The telescope was methodically scanning the sky as part of the search for extraterrestrial intelligence, a patient, monotonous task. The printout that night was a long string of letters and numbers representing signal intensity, mostly a sea of quiet background noise. Then Amon's eye caught a sequence so powerful and so strange that he circled it in red pen and wrote one word in the margin: wow. The signal, originating from the direction of the constellation Sagittarius, was a narrowband radio burst precisely at the frequency of neutral hydrogen, 1420 MHz. This is a quiet channel in the cosmic radio spectrum, a frequency many scientists had suggested would be ideal for interstellar communication. The signal lasted for 72 seconds, the exact duration the Big Ear telescope could hold a fixed point in the sky, and it displayed the telltale rise and fall in intensity as it passed through the antenna's field of view. This was the signature of a distant, localized source, not a terrestrial glitch or a natural cosmic event. It was everything researchers had been hoping to find, a perfect candidate for an artificial broadcast from another star. Yet when astronomers pointed their dishes back to that same patch of sky, again and again, they heard nothing but silence. The wow signal never repeated. It remains one of the most tantalizing and enduring mysteries in the history of SETI, a single, brilliant flash of possibility that vanished without a trace. It was a rebellion against the crushing quiet of the cosmos, a moment where the data seemed to shout that we are not alone, only to retreat back into an enigmatic silence. This pattern of fleeting, unverifiable signals has repeated itself. Decades later, in 2015, Russian astronomers detected another powerful signal from a star known as HD 164595. Dubbed the SHGB 02+14 a signal, it also appeared to be narrowband and artificial, sparking a new wave of excitement. But like its predecessor, it was never heard again. Other anomalies have surfaced, brief bursts of energy that fit the profile of a technological beacon before dissolving into the background static of the universe. Each one is a ghost in the machine, a siren song that pulls us toward the edge of discovery before fading away. They represent the ultimate cosmic tease, brief ruptures in the expectation of solitude. These unconfirmed signals are the whispers that keep the search alive, the haunting possibility that someone or something is trying to get our attention, but their messages are either too rare, too distant, or too brief for us to comprehend. They force us to live in the tantalizing space between noise and signal, between random chance and deliberate contact, forever wondering if the next blip on the screen will be the one that changes everything. But the story does not end here. It is merely entering its most thrilling chapter. Our tools for cosmic interrogation are about to leap forward in power. The James Webb Space Telescope peers into the infrared, allowing us to see the first galaxies being born, to analyze the atmospheres of distant worlds, and to watch the universe in its infancy. It will test the very foundations of our cosmic timeline, searching for the earliest starlight that could reveal flaws in our inflation story. Meanwhile, here on Earth, the Vera sea. Rubin Observatory will conduct a relentless, decade-long movie of the entire southern sky. It will map billions of galaxies, tracing the invisible webs of dark matter, and could discover thousands of new trans-Neptunian objects, finally confirming or ruling out the existence of Planet 9. These observatories will not work in isolation. Beneath the Swiss-French border, the Large Hadron Collider and its future upgrades will smash particles together with ever greater force, searching for any slight wobble, any anomalous decay that could point to the hidden particles tweaking the muon's magnetism or constituting the dark universe. We are building a new generation of eyes from the orbital to the subterranean, all aimed at these points of cosmic rebellion. The hope is that one of these machines will deliver a eureka moment, a single, clean piece of data that resolves the Hubble tension, identifies dark matter, or explains the lithium deficit. Yet the history of science suggests a different, even more exciting path. Every time we have answered a fundamental question, we have not found a final, simple truth. Instead, we have peeled back a layer to reveal a deeper, more complex, and often stranger reality beneath. Newton's clockwork gave way to Einstein's relativity, which itself gave way to the quantum weirdness that still baffles us today. Solving the mystery of the galaxy's spin revealed the ghost of dark matter, and explaining the universe's uniformity required the violent spasm of inflation. Each answer has been a doorway, not a destination. The pursuit of these cosmic anomalies is the very engine of discovery. It is the persistent itch of not knowing that drives us to build better telescopes, dream up wilder theories, and push mathematics to its breaking point. The universe's capacity for rebellion seems endless because our capacity for curiosity is limitless. The greatest discovery may not be the resolution of a current puzzle, but the unveiling of a new one, a phenomenon so bizarre it challenges a law we currently consider unshakable. The next great surprise is waiting, hidden in the data of a new telescope or the debris of a particle collision, ready to once again break the rules we thought we knew. From galaxies spinning in defiance of gravity to particles whispering across the void, these cosmic rebellions reveal a universe far wilder than we ever dared to imagine. Each anomaly is more than a simple error in our calculations. It is a brilliant signpost pointing toward a deeper, more complete understanding of reality. Dark energy, the black hole information paradox, the ghostly connection of entanglement, they all challenge us to think bigger, to question our most basic assumptions, and to embrace the vast unknown with courage and curiosity. The cosmos is not a static museum governed by a fixed set of rules, but a dynamic, evolving puzzle, a living story that is still being written. Let these stories of cosmic defiance inspire you. The next time you look up at the night sky, see it not as a placid map of distant lights, but as a frontier of mystery, a canvas for the next great rebellion waiting to be discovered. Never stop asking why. If this journey to the edge of physics has sparked your wonder, subscribe for more deep dives into the universe's greatest mysteries. And we would love to hear from you. Share your favorite cosmic rebellion in the comments.